Hey guys, welcome to Great Learning. Now, clustering is such an important part of machine learning, and in fact, it's such an important part of all the domains around us, right? When you think about where we use clustering, in fact, what is clustering, how we go about using it, once you figure out all the fundamentals, you will understand the importance that it brings to the picture, right? Now, clustering is a concept, ladies and gentlemen, that I can promise you that you've used it in your real life, right? Be it in your school, be it in your college, or even in your daily lives, I am very sure that most of you all, if not all of you all, have used clustering to a certain extent, right? Now, what's important for you to understand is the amount of impact that clustering has on the world around us, right? When we usually try to think of learning a new technology, learning a new domain, or learning such a niche concept in the world of machine learning or something like that, you really have to know why it is that you're learning, what is really important about it, right? Hierarchical clustering has a very, very important role to play in many parts of machine learning, many parts of unsupervised learning, and a lot more. So we're going to be taking a look at a lot of things hierarchical clustering, and it is really, really important for a person who's aspiring to look towards machine learning or who's looking forward to understanding all these concepts in depth, right? So keeping all of these in mind, understanding the importance of teaching you guys hierarchical clustering, we here at Great Learning have come up with this course to help you guys get started with the fundamentals, and at the same time ensuring that you have complete knowledge to build your foundations and eventually start working from there, right? So guys, without further ado, let's get started with this course. I welcome you all to this course. My name is Anirudh Rao.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.
Right? So on this hierarchical clustering course, we're going to start this out by taking an introduction to understanding what hierarchical clustering is. Now, once we have to really get rid of all the fundamentals, I'm very sure once we start discussing clustering, you might be a bit more confused. You might be looking forward for a direction to understanding it, right? So let's take an introduction. Let's dive down even to the most simple, the most basic examples. I'm going to be giving you guys a lot of examples while teaching you this. And of course, as soon as we're done with the fundamentals, the basics of it, you'll be very curious enough to understand what are the various types of hierarchical clustering that's out there. There's not only just one type. When someone says hierarchical clustering, it's not just one process that gets followed. There are various types of it. So we're going to be taking a look at that as well. And as soon as we are done with understanding the various types of hierarchical clustering, we're going to be taking a look at something called as agglomerative hierarchical clustering, right? Now, once you understand all of that, agglomerative, divisive, all of these become super easy for you guys. So we're going to understand how that works. And once you figure out what clustering is and how it works, you will find out that there are various ways through which you'll be bringing different elements together, or in fact similar or non-similar entities together to eventually create these clusters, right? There are many ways to go about doing that. We're going to be discussing 5 really important ways of how you can do that. And once you want to start working with clusters as a beginner, you must have this question. It says, okay, so now I know what clustering is, I know what its types are, I know what are the ways to find out similar and dissimilar measures. So what's next, right? The next question you're supposed to be asking is, how do I know how many clusters that I have to create, right? Now, when I'll be giving you examples, you'll realize that there's more than one way of how you can approach a problem and eventually solve the same too, right? So we are going to be working on understanding what is the best way of picking up, the best number of clusters that are out there, which will eventually help put an efficiency mark on an already efficient process, right? That's what machine learning is all about. That's what the spirit of machine learning is all about. And since we're talking a lot about machine learning, you will understand that hierarchical clustering has to play, it actually plays a very important role there. So guys, with this, I hope we are clear with all the points on the agenda today. So without further ado, I think we can get started, right? Well, let's get started with introduction to hierarchical clustering. Now, ladies and gentlemen, before we even go on to discuss hierarchical clustering, I think there is one important thing we have to discuss, right? What is clustering? Even before we talk about the hierarchical part of it, what is clustering as is? Now, clustering is a very simple process. In fact, it's a very popular technique in machine learning. Let's just talk about the reality of the situation. Clustering is a very simple principle wherein you would have a large data entity, a data group. You would eventually group it into entities or objects which have similar or dissimilar properties, and eventually that becomes a cluster, right? Now, I'll give you a very simple, a very broad example. Think about your days in school, right? When you were in school, whenever you asked a kid or whenever you asked your friend or someone, what do you want to become when you grow up, everyone sort of has their own say, and some say I want to become a pilot, the others say I want to become a software engineer, all of those things, right? Now, as in when you grow up, if you keep the same students, the same kids in your mind and you start tracking what happens to them, at the end of it, you'll figure out that a couple of them are software engineers, a couple of them may be pilots, a couple of them may be doctors, right? So we are basically creating clusters out here. If you remember, we just took a bunch of kids, a bunch of children, and I said, hey, okay, so based on what their goal is, or based on if they actually achieve that goal in their life, let's just split them out into their respective domains. So all the doctors on one side, all the engineers on the other side, architects on the other side, right? So you're basically taking a large data element, creating small groups of it. And what do each of these groups consist of? Each of these groups consists of the entities and elements. And why are they there? They are there because they have a similar property to everything around them. Now, if you just pick up one cluster full of engineers or full of doctors, what is the common thing there, right? The commonality lies in their profession. The commonality lies maybe in their interest. The commonality lies in the fact that all of them are probably working towards the same domain or working towards maybe a similar goal or something like that, right? So when you think about it, clustering is really one of these concepts which seems harder, but it's very simple, right? I'll give you another example. What about me giving you guys a couple of pens and a couple of pencils, all of different colors, and me telling you, hey guys, I want you all to just keep all the red colored pens and pencils on the left, all the orange colored pens and pencils on the left. So I'm going to give you colors and I'm going to say, hey, can you just make groups of all of these? Don't you think you can do it? Of course you can do it, right? So whenever you're given any sort of data point, grouping all of that into a certain number of clusters, wherein, each of these data element, each of these points have their own meaning, have their own understanding, and, each of these clusters are basically to a certain extent unique with one another, right? Because if when you're thinking about engineers, there's software engineers, there's mechanical engineers. Now, all of these guys are also in the same engineer cluster. So when you start digging into the detail, that's when you'll start figuring out maybe you can do more clustering. That's the advantage of clustering, to be honest with you. The way in which you approach the data, the way in which you track attributes to create clusters is not the end of the story. In fact, in many cases, you can use that approach to further dive into the depths of your data to eventually perform any sort of analysis that's required, or maybe you understanding your data for the concepts of feature engineering or something of those sort, wherein the data better to a point where you can have your machine learning algorithm work wonders on it, right? So that is really important for you guys to understand with clustering. Now, clustering is a very, very important part of machine learning. I think I've said that 3 times now, and probably I'm going to say it a lot more times. We say that it's because of the fact that whenever you are working on any sort of analytics project, right, be it exploratory data analysis, be it any sort of data analysis project that you're working on, there is multiple steps through which we go on to work with the data. Firstly, we ingest the data, as in we bring the data into our working environment from multiple sources. It might be Twitter or Facebook, competitor data, whatever it is. Now, once the data comes into your system, your architecture, you would understand that data is not really a very clean entity, right? There are many, many things which are of absolute use to your data, and there are some things which are again absolutely useless as well, right? You might say, hey, okay, so my data consists of a majority of things which are useful and a small amount of things which are useless. So let's just leave the useless part to it, right? Let's not bother with it. What could happen? The thing what could happen is for the fact that your machine learning algorithm is going to be learning all of these concepts from absolute scratch, right? If it's learning from scratch, it means for the fact that it can learn wrong. And if it can learn wrong, and if you're asking it to perform correct predictions at the end of the day, that's not going to go down really well, right? Because when you think about it, your machine learning algorithm has learned 1 plus 2 to be 4. And when you say, hey, why is 1 plus 2 not equal to 3? It says, I don't know, because that's what I've learned, right? I mean, of course, it's a very hypothetical example, but these techniques are very critical, and especially on the lines of data cleaning and data preparation, clustering is very much there, right? Data cleaning, data preparation is a step that happens before we go on to perform any sort of data analysis. And in this step, this critical step is where clustering comes to the picture, and there are many clustering techniques that gets carried out here. Because once you start understanding your data, and once you figure out that you can probably simplify your data into maybe smaller chunks, into better chunks wherein you have more clarity of understanding the data yourself, and of course that directly translates to the fact that your machine learning algorithm can also understand the data better, right? And that is a very critical part of it, because if you do not go about thinking on the lines of these, again, your machine learning model or your machine learning algorithm can actually, while training itself, you might see a lot of inconsistencies in terms of its accuracy, you might see a lot of hits and misses in terms of its performance, and a lot more, right? So in machine learning, I'm sure if you're watching this particular course, you will be clear for a fact that there are 3 ways in which machine learning algorithms learn, right? The supervised learning, unsupervised learning, and reinforcement learning. Now, clustering falls into a part of unsupervised learning. I'll give you a quick difference between supervised learning and unsupervised learning. What happens in supervised learning is that we provide the data for training, and we also provide labels associated with the data. So if I'm giving a couple of pictures of cars to my computer, to my machine learning algorithm, I tell the algorithm specifically saying, hey, I am 100% certain that this is a car. So understand what a car looks like, and eventually start figuring out other cars, right? It already has 100% verifiable data point through which it can learn, like a textbook, for example, if you guys are students in your college, right? So unsupervised learning is slightly different. In unsupervised learning, you're not providing clarity on what data you're providing to it. In fact, you're asking the machine learning algorithm saying, hey, here is some data for you. Here's a picture of a car, but of course, your machine learning algorithm does not know it's a car. What I'm going to say is, instead of just directly matching this with other images or something of that sort, what you do is you figure out the structure that is present in the data, right? Whatever is happening inside your data, what leads to a car. A car should have 4 wheels, it has to have an engine, it'll have a couple of windows, it'll have a windscreen, all of that, right? So your machine learning model, in the case of unsupervised learning, will actually hunt for these structures. It'll try to understand what is going on in terms of what image it is looking at, what patterns it can understand, and all of that, and later it eventually uses that to learn and build upon, right? So in the case of unsupervised learning, in the case of clustering as well, since it's unsupervised, we do not provide any sort of class, we do not provide any sort of labeling or any sort of target variable and say, hey, you're going to be modeling based upon that, right? So what we are trying to do here is we are very much interested in grouping similar records, grouping similar objects into a cluster, and then eventually using this cluster to go about understanding how things progress and how you can work with your data better, right? So guys, that is a quick introduction to give you guys an understanding of clustering. But let's actually, since we're talking about clustering, since we're talking about machine learning, and since we're talking about the real world, I think it adds a lot of value for you guys to actually, learn this using a practical approach, right? So here I have a very simple example trying to teach you clustering by taking the example of a retail use case study, right? A retail domain use case study. Now, let's just say there's a retail chain. They're a very expensive, high fashion chain maybe, and they are trying to segregate their customers into 3 categories: low income group, medium or middle income group, or of course you have the high income group, right? LIG, MIG, and HIG. Now, based on their sales data, you can actually perform to a certain extent an accurate classification, right? Think about mobile phones. Now, there's a lot of mobile phones in today's world where it probably starts at 5,000 Indian rupees and goes all the way up to, I think, 1,80,000 Indian rupees or something like that on the higher end spectrum, right? Now, Not everyone would be able to afford the most expensive mobile phone out there, and there's another group who would not want to buy the cheapest mobile phone they could probably find, right? Maybe because they have an income source through which they can comfortably afford a very expensive device. So once you start classifying it and once you start dividing these customers, saying, hey, these people belong to maybe a lower income group. I mean, no offense, this is an actual a classification. This happens everywhere around the world, right? So splitting data, finding all your middle income group people, putting them into one class. When I say class, it's basically a cluster, and eventually finding all the people with middle income group and eventually grouping them to one side, higher income group, putting all these folks into one side, right? You can take a look at the image on the right side of your screen right now. We had a bunch of customers, right? These stars, triangles, and circles. And what we did is we took the bunch of them, we understood, we analyzed, we performed some basic analysis even before clustering. We figured out who the lower income group people, who are the higher income group, the middle income group people, and we eventually just filtered them out into those clusters, and we gave them their own space, we gave them their own bubble for the machine learning algorithm to work, right? So the objective of clustering is basically for a fact that we are trying to pick up multiple different types of customers here, and we're trying to separate them, or we're trying to create groups of them through which we can perform some analysis. And of course, as you can see on your screen, this is what is mostly clustering, right? So you can see that the pink, blue, and the yellow circles out there are data points in which you have three clusters: low income group, middle income group, and higher income group. And these people in there might have similar shopping habits. These people, might be for a fact that they are a homogeneous collection of customers, as in you will find in the real world itself, right? There are certain people who will just stick to one brand of mobile phone no matter what, be it OnePlus, be it Apple, or whatever it is. I think the informal term is fanboys, but they do prefer the loyalty to that brand. So you can pick up all of those people, put them in a cluster and say, hey, these people prefer OnePlus devices. Now you can pick up another group of people and say, hey, these guys are total fanatics when it comes to owning Apple products, so let's put them in a cluster, call them Apple customers. Don't you think that can work? That can absolutely work, right? So this is all about clustering. But you might be asking a question at the moment right now saying, okay, clustering is absolutely fantastic. Talk to me about hierarchical clustering. Hierarchical clustering is a similar situation, but here what we're trying to do is we're trying to create clusters in the form of a hierarchical tree-like structure. This tree-like structure, you might have heard it elsewhere. It's also called as a dendrogram, right? Now, a dendrogram basically is talking about how you can break things down into simple structures, and in this case, a tree-like structures, right? Now, we're going to take a look at a lot of examples, don't worry. So, to talk about hierarchical clustering, here as well, we are going to be taking a similar set of data points and we'll be creating a tree-like structure out of it, in which there's a root node, there's multiple other leaf nodes as well, right? So the root node corresponds to all the data that is present, and individual branches is basically the cluster that we're talking about, right? If you've seen a decision tree or if you've seen random forest, you will understand the approach that I'm trying to tell you, right? You have a tree, you have a main node, or it's called as a root node, and from that you have multiple different branches. In our case, in the case of hierarchical clustering, the main node or the root node will basically have all of the data. And once we try to take all of that data and split it out into multiple branches, what do you think we're doing? This is where we're performing hierarchical clustering, and since we're doing it in a tree-like structure, that is how it gets its name, right? It's a pretty simple concept. Now, we've understood what hierarchical clustering is, we understood what clustering is, why we require it, how it talks towards machine learning, and we understood a good amount of bit about clustering and hierarchical clustering. The next thing you'll be very curious to figure out is what are some of the various types of hierarchical clustering that's out there, right? So without further ado, let us quickly discuss some of these really interesting types of hierarchical clustering out there. There's two very important, very critical types of hierarchical clustering. There's called as divisive hierarchical clustering, and they're called as agglomerative hierarchical clustering, right? Now, if you can figure out the meaning in the names divisive and agglomerate, you can actually figure out what it means, right? If you couldn't pick that up, I'm going to tell you what each of them mean. So let's get started with the first one, which is divisive hierarchical clustering. Divisive hierarchical clustering is an approach which we would call as divide and conquer, right? So it's basically an approach where we are considering the top-down clustering approach. What happens here is that all of our data, all of the observations, everything that we absolutely have, we'll just put it out to one cluster to begin with, one big fat chunk of cluster, right? All the data elements, all the points. what we do later, since the name itself suggests divisive, we have to divide it into clusters, right? So we're going to be basically splitting it based upon, certain condition, based upon some observations, or based upon certain similar characteristics. We'll be splitting it into further clusters and giving room for each of these data points or each of these observations to have their own clusters, right? Very similar, I can give you an example. If I just give you a basket full of fruits, some of those fruits are not yet ripe, they're raw, and some of those fruits are ripe, they're ready to eat. If I just mix them up in a basket or in a bag or something, and I give it to you and I say, hey, can you just put all the raw fruits on the left side? Can you put all the ripe fruits on the right side? You'll do it. The next thing I'll say is, hey, let's just go to all of those, we'll just go to the cluster where there are raw fruits. Now, can you separate that out based on the type of fruit, right? So you had all fruits, now you have raw fruits and ripe fruits. In the raw fruits, you're going one more step into it and saying that let me separate all the raw apples, let me separate all the raw oranges, let me separate all the raw peaches, or something like that, right? So you are just going and creating sub-clusters, and all of these sub-clusters, where did it begin from? Where did it start? It all started out from one big chunk, right? So we are working down, top down. We're taking a top down approach to work towards it. We're taking one big entity and we're eventually splitting it into multiple small entity, and that, in the name as it suggests, is divisive hierarchical clustering, right? That's one type. We have another type. This is called as agglomerative hierarchical clustering. Agglomerative is almost a complete opposite of divisive, because what we are trying to do here is we're taking up a bottom-up approach wherein every single data point that we see, every single observation that we see is a cluster of its own, right? In the top-down, you have all the data through which you sort of split it and break it down into its clusters and assign it groups and all of that. But in the bottom-up approach, what we do is every single element that we will come across, we'll say, hey, you're a cluster on your own, go enjoy, right? So we're going to give it that cluster status, and eventually we're going to work through all of these clusters. And here, instead of arriving at multiple branches, we are working our way back up the tree, and we will arrive at what? We will arrive at one big cluster at the end that eventually consists of all the data, right? So it's basically us figuring out two different ways to come around the same problem. And if you're wondering, saying, hey, why do we have to do that? Doesn't just divisive do the job for us? Why do we require agglomerative? Well, for a fact that there are many cases when you're working with machine learning, right? When you're working with a large amount of data, practically, you will come to a point where you might feel, hey, this type of clustering might not really work, because maybe your machine learning model is underfitting, it doesn't know what's going on. Maybe then you can figure out an approach to say, hey, maybe I can use agglomerative, right? Maybe I can treat each individual data point as a cluster of its own, so that when we build up across multiple clusters to that one big element, that is where maybe you can have more meaning. That is where your machine learning algorithm will be able to do what? It will be able to connect the dots better to understand, right? That's all the goal. That's everything that we're trying to do. Get your machine learning algorithm to work better and give you a better model's output, right? So, as I just told you, right, one thing you have to understand is that agglomerative and divisive hierarchical clustering, these are sort of very different approaches, because it almost does a 180, right? It almost does exactly the opposite. In one case, we're just taking everything from one big chunk, creating multiple branches, and in the other case, we are creating multiple branches, and we're eventually ensuring that all of that lead back to one big chunk. Now, it's exactly the vice versa as you figured it out by yourself, right? Both these are very different approaches, but one thing you have to understand is that when we're talking about applying hierarchical clustering for multiple reasons, you have to understand that the goal will mostly be the same to, getting your machine learning algorithm, or just figuring out how better, you can work with your data as well, right? So that is something which is very important for all of you all to understand. Right, now that we had a chance to take a look at the various types of hierarchical clustering out there, divisive and agglomerative, I think the next question you might have, divisive is very simple, right? You have one big chunk of data, you just split it out into multiple pieces, and you keep doing it until the requirement is satisfied, or until, your goal of what's required of the data is met. So you might have a question that says, okay, so how does agglomerative hierarchical clustering work? How do we go reverse in this process, and how do we go about building up into one big thing, into one big event, into one big cluster, right? Well, let's take up examples to understand how agglomerative hierarchical clustering works. Because when we are talking about hierarchical clustering, most popularly, even though it feels like divisive is the widely used one, it's actually agglomerative because of the sheer advantages it provides, as you guys will figure out going ahead. So quickly taking an approach to understanding what agglomerative hierarchical clustering means and how we can figure it out, let's consider a set of n observations to be clustered. Right, we have multiple observations. We know that these have to be clustered. So what do we do in hierarchical clustering, right? First step is to assign each and every observation point that you have a cluster of its own, right? You give it a single point cluster of its own for n observations. So if you have n observations, and if you're telling them, hey, we're going to give you a cluster of your own, what do you have? You have n clusters, right? N clusters basically, and each of these containing just one single observation. One cluster, one observation. Similarly, you have many clusters, right? If you have n data points, you have n clusters. Now what we do next is the fancy part. We find the closest, in fact the most similar pair of clusters, and we make them into one cluster. We just find 2 points which are very similar to each other, and we say, hey, you guys don't have to be 2 separate clusters, you can become one cluster, right? And what do we have? We started out with maybe 100 different data points. We had 100 clusters. Now we merged one of them, and now what happens? Now we have 99 clusters remaining. We have n minus 1 clusterings, right? Now this process, ladies and gentlemen, step number 2 that you're seeing is very critical, since this is the entire heart of hierarchical clustering. There's many ways. Now you're supposed to be asking me a question. You're supposed to be saying, hey, okay, so you said that, hey, we're going to find out similarities between 2 clusters, and we're going to either merge them, or we're going to find 2 very dissimilar clusters and push them apart. How do you do it? How do you figure out, these clusters are either similar to each other or not similar to each other, right? This is where the magic happens. This is what will be the rest of our discussion for this course as well, right? So anyway, coming to step number 3 now. Step number 3, what we do next, once we figure out two of the closest clusters and make them into one, is we keep doing it for a while, right? Now you had 100 clusters, you merge one of them, you have 99. The next step is to basically merge that cluster with another cluster. Now what do you get? You started out with 100, you came to 99 clusters, and now you have 98 clusters because you eventually got 2 other clusters to mix up and become into one big cluster, right? So this is a concept basically called as agglomerative clustering linkages, where you're trying to link each of these data points. You're basically giving each of them some meaning. You're calling them as clusters. You're bringing together clusters, or you're moving clusters away because they're dissimilar or something like that. And basically most of the concentration happens on the clusters that you bring together, and that is for a fact of how you would go about doing hierarchical clustering, especially agglomerative hierarchical clustering, right? Divisive is simple. Just take the entire data approach, cut it down into simple clusters, and you're done. The backwards approach that we're taking in agglomerative is the one that that gives you, I'm going to say, more powerful results, but that's a very vague statement, because at the end of the day, there are cases where agglomerative doesn't work as good as divisive. There are cases where divisive works really well, agglomerative also works well, and the vice versa might not be that great, right? So it is completely dependent on the application that we're working on, but the fact that we have these options are the ones that are helping us make machine learning a better technology, right? Take a look at agglomerative clustering. Step number 0, right? Step number 0 is where you have each of these entities to be single elements on their own. So what we did is we took a couple of letters and we said, hey, we're going to give you a cluster of their own. You can see that U has its own cluster, W has its own cluster, X, Y, Z. All of these have their own clusters. And the next thing, at the first step, I'm going to say, hey, U and W, I think you guys are pretty common. So let me just merge you guys into one cluster. Works. The others, you don't have to compulsorily do that. You're only doing this if you have certain similar characteristics, or if you know that certain set of observations will give you a critical output, right? And then you go to X. X, well, maybe it is not similar to anything else, so you just keep it that way. Y and Z, maybe in step number 1 you couldn't see a connection, but when you're doing it again, you see another connection, you say, hey, okay, so Y and Z, I think you guys are similar as well, let's bunch you up. And once you bunch up Y and Z, X was remaining, right? So now maybe the pattern unveils itself enough where you figure out saying, okay, I think now we can add X into this cluster as well. So what started out as U, W, X, Y, Z now has UV as one cluster, YZ as one cluster, and YZ along with X has formed another cluster, and this cluster is XYZ. And once you bring that together with UW, what do you have? You have UW, X, Y, Z. Give that a thought, right? So we just went from each individual clusters, we just started grouping them based on certain characters. In this case, it's a random example, right? There's no characteristic that makes y and z equal or something like that, but we're going to be repeating these steps, right? The steps that I told you, step number 2 and 3. If you haven't taken a screenshot or taken note of this step, make sure you do it. It's very simple for you to understand, but at the same time you can get confused as well, right? So we're going to be repeating this entire process, wherein we will be repeating 2 steps until all the observations that we have are clustered into what? Not into many clusters, because that's how divisive works. In agglomerative, we're going to take multiple clusters and the goal is to create one big cluster, right? Now, with that, I am confident that you guys understand to a certain extent how agglomerative hierarchical clustering works, right? So here, what we basically do is we use various distance similarities and dissimilarity measures to understand how we can first of all create these separate clusters that we out there, that we can go on to create there. And once you figure out the various clusters out there, you'll be like, okay, maybe data points are similar if 2 clusters are placed closer to each other, right? Maybe if you're marking them on a timeline or anything, these 2 points can be very, very close to each other. Now, when that happens, you can say, to a certain extent, you can think of the fact that saying, okay, since these are very close and, very close by to each other, let's just merge them into one, right? Once you go on to do that, you can group all of that into one large cluster and we can go about with the process of hierarchical clustering. So more the similarity, better the chances of you creating that cluster, maybe merging clusters faster and getting to a point where, you can go on to have these big clusters at the end. But as I told you, right, step number 2 is very elusive for a fact that you can just say, hey, I'm going to find 2 similar data points, or I'm going to find 2 similar data points and I'm just going to bring them together. Wonderful. How do you know these 2 points are similar? How do you know that you have to group them? Why can't you group them with something else? Why do you have to do it this way? Will be a lot of questions that you guys are asking, I'm sure. Well, to answer that, we have multiple methods. We use various techniques through which we can do step number 2. What was step number 2? Step number 2 was us trying to basically figure out how we can bring together multiple clusters to create one big cluster, and that process of us merging, the process of us finding similarity or us finding even dissimilarity to a point where we can split out 2 clusters, separate them, move them far away from each other. It can be done using concepts such as Euclidean distance, Manhattan distance, the Minkowski distance, the Jaccard similarity coefficient, and the cosine similarity as well. Now, I am confident that some of you all might have heard these terms. You might not know what they mean, you might not know how they have been used, or you might not know how it even talks to the world of machine learning. Well, now, just with this slide, just with learning for the last 35-40 minutes, you guys have come to know what these are, how they can be used, and in fact, where it is critically used in today's world. So the next time someone asks you what's the use of Manhattan distance, what's the use of Minkowski distance, Minkowski as it's called, you can actually go on to give them an answer now. How fantastic is that, right? Well, I think it's high time we take a look at how we can go on to create these clusters, and the first way to go about doing it is Euclidean distance, right? Now, ladies and gentlemen, Euclidean distance is really fun to learn because this is very widely used. Whenever someone talks about agglomerative hierarchical clustering, Euclidean distance is the go-to point, is the first point that they go on to, right? It's widely used because what we do here is whenever we have variables which are continuous in nature, maybe there's a strong interval or there's a ratio or something like that, right? To give you a sharp interval, just think of an example of maybe your age, right? With every passing year, you just become 1 year older. You don't go around the sun once and say, hey, now I'm 3 more years older, right? I was 21, but next year I choose to be 25. That doesn't work, correct? So that is something you have to understand here. And whenever you're trying to calculate the distance between 2 points to say, hey, if they are similar or if they're not similar, you actually consider calculating the length of the segment that connects these 2 points, right? There are 2 data points plotted. You want to figure out if you can bring them together. To bring them together or not, you have to find the similarity to it. And to find the similarity, you just find out the distance that lies in between these 2 data points. And using that distance, you eventually can go on to figure this out, right? The most mathematical way, the most fundamental way, and the way that works is Euclidean distance, right? Because you're measuring how far these 2 clusters are, and eventually if you have a situation, a condition wherein you can say, hey, if the clusters are this close apart, XYZ, that's a point. If it's that close apart, bring them together and make them into one cluster, right? That is Euclidean distance. So as I told you, right, you can find similar and dissimilar measures, and whenever you have two data points, what do? The Pythagoras theorem is extremely popular to calculate the distance that exists between 2 points, right? Take a look at the figure. X1, Y1 is one of the points. X2, Y2 is one of the points. We know for a fact that we can find D as a square root of X2 minus X1 the whole square plus Y2 minus Y1 the whole square. How do we know that? That's Pythagoras theorem, right? So in the three-dimensional space, you can find the Euclidean distance to actually be the square root of x2 minus x1 square, y2 minus y1 square, and z2 minus z1 square, right? Now you're going to be adding all of these. First of all, you're going to take the squares of it, you're going to add all of that, and eventually you're going to take one big square root of all of that, and that will give you the Euclidean distance, right? Very simple concepts. Two data points, find the Pythagoras theorem, find the straightest, shortest distance between these 2 points, find out what the distance is, and eventually use that to make an assessment later on, right? Don't you think the concept is very simple now? I am sure you feel the same, right? So that's Euclidean distance. We have another way to go about doing this. It's called as the Manhattan distance. So what are we talking about in terms of Manhattan distance? Well, if Euclidean distance is a basic method and if it just works, why not go on to use it for everything? I'll tell you why it cannot work. Euclidean distance, in some cases where you have to find the distance between multiple points where the locations of these are very different, Euclidean distance will fail to work there, right? It's not like you can just draw a triangle everywhere, use the Pythagoras theorem to find the straightest line, and you're done. Sometimes your data will not align for that fact. So that is when, maybe I'll give you an example, right? Think of a situation where you have to find the distance between two retail stores in your city. In this particular case, there is not many cases where you can draw straight lines out of it because you have streets, you have crossings, you have whatnot. So in this case, instead of just drawing a straight line from this to that, you can actually have Manhattan distance. In fact, that's how it gets its name as well. It is a better way to figure out the distance between these two retail stores that you're trying to measure, right? So the distance between these 2 points in a grid are completely based on two things. One is the vertical path that you can take to that particular grid, to that particular point. The next one, as you would have already guessed, is the horizontal path that you would take, right? So we know that it's different from Euclidean distance. We know it works better than Euclidean distance, but what are we doing at the end of the day? Well, at the end of the day, it's a simple process of us taking the simple sum of both of these vertical concepts, vertical components, and the horizontal components to get us to that, right? Take a look at the image on your screen. As you can take a look at it, an Euclidean distance is basically a straight shot line that says, hey, find me the distance between that and that. But Manhattan distance talks about 2 points being at two different locations. Look at that, it's not in a straight line, right? So for this particular case, we can say for a fact that the Manhattan distance is nothing but the distance that you would take to go around traveling that particular coordinates, right? You can see this example with the triangle, right? 6, 5, 3. Once we go on to perform the Pythagoras theorem, and once we go on to take a square root, you get a square root of 25 plus 9, which is the square root of 34. The square root of 34 will give us what? 5.83. Great. Now let's go on to find the Manhattan distance. Manhattan distance talks to us about saying x2 minus x1 plus y2 minus y1. So x2 is what? 9. x1 is what? 4. y2 is 7. y1 is 4. So once you do the similar calculation, you get 5 plus 3, which is 8. Now, Manhattan distance in this particular case is a better way to go about accurately finding the distance between these two data points. And this example showcases that really well, because for a fact that we have taken the same example to tell you how Euclidean distance works, and the same example to tell you how the Manhattan distance works as well, right? So I hope these both are clear to all of you all, right? Now on that note, we can go on to take a look at the next way of how we can group these clusters or move clusters away. That is the Minkowski's distance. Now there's many ways of how you can spell it. I usually prefer saying Minkowski's, where the K is almost silent. Minkowski. You can go on to work with that any way you want. Now, Minkowski distance is very similar to Manhattan distance. What we're trying to do is, again, we're trying to find the distance that lies between two variables. In this case, let's consider the variables are x and y. If you have your variables as x and y, you'll see this very complex formula on your screen. It's not actually very complex. You see this variable p, right? Whenever p is in a situation where it's 1, basically we're saying, the Minkowski's distance is equivalent to the Manhattan distance. When that becomes 2, we're saying that it is very similar to the Euclidean distance, right? So the magic lies in the p values, the magic equally lies in the x and the y values. But when p becomes 1, you have to understand the Minkowski distance is very similar to the Manhattan distance. When the value of p becomes 2, what happens then? Well, then the Minkowski distance is actually equivalent to not Manhattan distance, but to Euclidean distance, as we covered, right? So Minkowski's distance, is a league of its own. It will, in my opinion, this is a way of doing a certain thing when you have ascertained other facts, right? You know how Euclidean works, you know how Manhattan works, and you want to find a method through which you want to use these two methods better. That method is Minkowski's distance, right? It's a very simple, very straightforward concept. Now, at this moment of time, I believe that there is no need for you guys to go extremely in-depth analyzing how this formula comes, how do we go about that. All of that is the theory that leads up to the point. What you guys should be focused on is for a fact that understanding how you can use this. First of all, knowing how you can work with the equation, knowing to a certain extent it does help, I can tell you that. To a certain extent it does help for you to figure out how and why we arrived at that. But most of your practical application will be figuring out not why it came about the way it did, but the fact that how you can use this to the best of your ability, right? That is very, very important. Now we're done with that, we can take a look at the next one, which is Jaccard similar coefficient, or it's also called as the Jaccard index. So whenever someone talks to you about the Jaccard similarity coefficient or Jaccard index, understand that it's one and the same thing, right? So Jaccard similarity coefficient is basically used, again, can be used whenever you have your data or variables, but in this case, instead of quantitative data, here we'll have qualitative data, right? So there can be situations wherein you have to figure out, be very divisive to a certain fact that your answer might be yes or no. It can be 0 or 1. It can be true or false, right? It can be a binary outcome. Now, these are not numbers. Of course, 0 and 1 are numbers, but yes and no, true and false, these are not quantitative data. These are qualitative data, right? So when you have those binary cases, it becomes very important for you to understand, saying, hey, we have complete two different cases. Where, how do we assess if there's any similarity or dissimilarity? Think of the concepts of sets that you would have learned in your school and your college, right? You find the union of it. You find the elements which belong to both the classes. Sometimes you go on to find the entity which just belongs to one of these classes and not both. The concept of us using the and or seems very familiar to you, right? When we're talking about and, we're talking about elements which belong to both the classes of X and Y. Once we're talking about or, it means it can either belong to class A or it can either belong to class B, in this case class X and class Y, right? So the Jaccard index is actually figured out by this. We take the area of the intersection and we divide it by the area of the union, which eventually gives us that, right? Now, you have to understand that the union has its own formula, X plus Y minus X intersection Y, or X all Y. Now, once you go on to take all of that and you apply it into a formula, finally you will get this formula which says X intersection Y divided by X plus Y. This is Jaccard's index. So whenever someone asks you, hey, what is Jaccard's index, Jaccard similarity coefficient, now you know how you can go about answering that question while telling them where and when it is critical to be used, right? So what we're going to do is we're going to take a quick example to understand this better, right? Let's just consider that there are two stores who are willing to sell the items that you see on your screen right now, and each of these is an element on its own, right? So store number 1 wants to sell bread, jam, biscuits, Coke, beer and a cake, and store number 2 wants to sell Coke, curd, butter, bread, cake, jam. Even though it seems similar, a couple of different items that it wants to sell, right? And once you go on to observe that, these are the different elements. Each of these are entities, right? Bread, jam, Coke. What do we do in agglomerative? We give them their own cluster, right? If that store has sold that item, we give it a 1, else no. Take a look at this, for example. Store number 1 sells biscuits, correct? Yes. So store number 1 gets a 1 under biscuits. But does store number 2 sell biscuits? Not really, right? So it gets a 0. So once we go on to map all of these elements out, we can go on to work with it further, right? So we figured out all of these. And one thing you have to understand about the Jaccard index is for a fact that once you perform the entire process, the formula will lead to a fact wherein it will give you a range that exists between 0 and 1, right? You cannot have -5 to be a Jaccard index. It wouldn't make sense. You cannot have +2 to a certain extent. That won't make sense as well, right? Okay, so now we know what Jaccard index is. How do you say if 2 points are similar? if this number that we're talking about is higher, the similarity will basically be higher, right? If your Jaccard index is very high, it means that the similarity between those two data points that you're talking about is extremely high. Very good chance you can put them into one cluster and be done with it, right? Very simple example. And performing the Jaccard index on this particular example gives us to a fact where it brings us to 4 divided by 8, which is 0.5. So 0.5, we're talking about a similarity saying, hey, there's a 50-50, there's a 50%, 50-50 chance that the store 1 and store 2 are selling each of these different items on their own. Right? Coming to the last one, we have cosine similarity. Now, ladies and gentlemen, cosine similarity is a very, very important measures, because here we'll not consider the data points as scalar anymore. We're going to be considering the data points as vectors, right? So the cosine similarity formula is as you can see on the screen. And do not worry if you cannot figure out what is happening, because there's a lot of summation that's happening, a lot of multiplication, all of that. Understand one thing: when you're working with cosine similarity, you know what it is that you're doing. You're going to be using a formula, and the output of this formula is basically going to give you a range that lies in between -1 and +1. And when we say, hey, what happens when your cosine similarity is low? It means that the two observations that we have, is it less similar or more similar? If your index is low, if your similarity is low, it means it's of course low, right? Similar to Jaccard's index here as well in cosine similarity. If your cosine similarity value, the eventual value you get between -1 and 1, if it is very low, it means there's absolutely no dependency. There's a similarity between these 2 points. But if the number is very, very high, it means both the points are similar. So I know it can get slightly confusing. So let me give you a beautiful example to clear it out completely, right? So let's just consider that there are a lot of shirt brands, right? So I think these are the ones that are super popular in India right now. And we have 2 customers who have bought shirts from all of these brands, and they've just given a rating, right? So whenever someone buys a shirt, you might have seen Amazon do this, right? They'll say, hey, please provide a rating to help us help better, something like that. So on a scale of 1 to 5, these customers have rated their own brand. So we have 2 customers who have given ratings across all of these 6 brands that you can see on screen. For example, customer 1 really likes Arrow, right? He has given a 5 out of 5 rating. Customer 1 maybe doesn't really like Zodiac. Maybe the patterns are not great. Maybe the quality of the shirt is not great. So he's given it 1. Similarly, customer number 2 is also very different in its approach. Customer number 2 likes Zodiac very much and doesn't really like Arrow or Alan Solly like customer 1 does, right? So taking a look at it, you'll find customer 1 and 2, their behaviors are very different, even though they're probably talking about the same brands. So when we go on to apply the cosine similarity on this, it's a very simple thing of how we apply the formula, right? You saw that very big formula which is confusing. Let me simplify it down. So all we're going to do is we have to find summation, right? We're considering it as vectors. So all we're going to do is we're going to multiply 4 into 1, add that into 5 into 2, add that with 3 into 4, 5 into 3, 2 into 3, 1 into 5. We're going to multiply each of these customers' opinion about that brand, add all of that into one element. Now, when we go on to do that, we get one number, which is basically 52. Right? And we have to find what's happening to only A. We have to find out what's happening to the only other cluster, right? So this is where we go on to take the individual squares of this. For example, with customer 1, you can take a look at it, right? So we have taken 4 square plus 5 square plus 3 square, 5 square, 2 square, 1 square. Similarly for B, we have taken 1 square plus 2 square plus 4 square, 3 square, 3 square, 5 square. We added these two different elements. For A, we got the score to be 8.94. For B, we got the score to be 8. Now what we do is we multiply these two options and we eventually arrive. Once we go on to see the final cosine similarity formula, as you can see in your screen, A into B divided by the individuality of A with individuality of B, you will see for a fact that we will arrive at what? We have arrived at a number. Look at this number. It says 0.72. What is the valid range for our cosine similarity? -1 to +1. Is 0.72 in that range? Of course it is, right? So basically we're saying these two customers might have, even though on the overall it looks like they have different patterns, but these two customers at the end of the day, when using cosine similarity, are showing somewhere around 72% worth of similarity. And depending on what number, what is the threshold that you want to cross to bring them into one cluster, you can take a decision right here, right? If you say, hey, I need 85% similarity to bring them together, in this case, you wouldn't bring these two together. If you were to say, hey, I need 70% equality, 70% similarity between these two properties, where if it is anything greater than 70 or anything greater than 0.7, I'm going to bring it together. In that case, you would, right? So this is the simple world of cosine similarity. So quickly coming on, to the last point of the discussion, how do you go on to find the optimal number of clusters, optimal number for clustering? Again, it certainly becomes a challenge, right? You would not know what to pick up, how many number of clusters to actually create. One challenging task in agglomerative clustering is for us to, of course, find out how many different clusters we're going to do. We have one more wonderful metric to go about tracking this. It's called as the silhouette score or silhouette score, however you want to spell it. Silhouette score is basically one of the most popular approaches that we take whenever we want to find out the number of clusters that we want to create, right? It is basically having a measure of how close each of these points are in a cluster and comparing that distance with how far away it is to its nearby neighboring clusters. Right? So this simple formula of finding the distance between all the points in one cluster versus finding the point, finding the difference that lies between the other points in the neighboring clusters is what will help us get to the optimal number of clusters, right? Let me give you an example for that. Let's just say AI is a metric where you have the mean difference between the observation I and the other point in the cluster through which each observation I is assigned, right? That is A. Then B is basically another minimum mean distance that happens to be occurred at that observation I, and all the points, it points to what? It points to the other clusters, right? So the formula is simple. It's BI minus AI divided by find the maximum in between AI and BI. So whatever point, whatever has the highest distance gets taken over, and eventually that is how you would take the entire point of all the observations BI minus AI divided by the maximum of AI and BI, and that number that you get, that is what? That is the silhouette score, right? And you might be wondering, hey, since we're doing a bunch of operations here, silhouette score can be anything. Not really. Silhouette score always comes into the range of -1 all the way to +1, right? In this case as well, higher the value of silhouette score, it indicates that your observations are really well clustered, that you have done a good job clustering this in the way that you have done. If your score is very high for 5 clusters, it means that 5 clusters is optimal. If that score is extremely high for like 10, 12 clusters, it means that that is the right amount of clusters you have to consider there, right? But you must be curious at this moment of time. If we're talking about a range between -1 and 1, you forgot to ask me saying what happens if it is 1. If silhouette score is 1, what happens, right? It indicates that whatever observation that you have at hand, it is a perfect match to the cluster assignment that you have done. As in, theoretically speaking, there could be no other better way to arrive at an efficient solution if you were to cluster it in a different way. So the clustering that you have done is absolutely fantastic, is what a silhouette score of 1 would tell you. So guys, with this, we have come to the end of this course. We discussed a lot about hierarchical clustering. So thank you so much for watching. To quickly summarize everything we have learned, we started this one out by going right back to the basics. We understood what clustering was. Once we figured out what clustering was, then we took a step into understanding where it is used, how it is used. I gave you a lot of examples there. After that, we made sure to take a look at understanding what is hierarchical clustering first of all. Once we understood hierarchical clustering, why we require that, what's the thing that's going on with all these clusters, we figured out that there's more than one way to go about performing hierarchical clustering. Divisive hierarchical clustering, agglomerative hierarchical clustering, right? And we understood what happens in divisive, it's a top-down approach. What happens in agglomerative, it's a bottom-up approach. And when we started diving into the depths of agglomerative, we figured out that it's as easy as saying these two are similar, bring them together. But in the mathematical terms, in a numerical metric, how do you prove with data that these two are similar? We figured out multiple methods to go about doing that. We took a look at Euclidean distance, Manhattan distance, Minkowski's distance, the Jaccard Index, Cosine Similarity. We took a look at so many ways of how we can go on to bring these clusters to its similarity, or if move them away if they are not similar, right? Now, you might have come into this course absolutely having no clue what hierarchical clustering is, but I promise you for a fact that if you've come to this point of time, you completely know, you have extremely strong foundationals and extremely strong fundamentals on hierarchical clustering. Now you know what they are, what are the various types, how you go about bringing these measures together or not, what are the various types, how you use them, where they use, and a lot more, right? So guys, I hope you guys had super fun finishing this course. Thank you so much for watching again. My name is Anirudh Rao, and as always, I'm more than excited to see you guys on the next one. Cheers.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.